Okay, welcome to class. We left off last time with last class having introduced that semiconductors are materials that have a band gap, and the Fermi level lies right in that band gap, but the band gap isn't huge. So if you give it some thermal energy or light or other things, you can take these carriers and you can excite them across the band gap, and we call that process intrinsic semiconduction. John?
So in an LED,
Good question. Is it a physical gap or what is this? No, that's not what the band gap is. That's a good question. This is purely speaking with respect to energy. We're talking about occupiable states at a lower energy, and then you've got a gap where you don't have states where electrons can occupy in terms of energy, and then you've got states where they can occupy. So in physical space, that electron's not moving, but it is gaining energy by going up to higher energy levels or not. Okay, so that was intrinsic semiconductions when you jump across the gap. At the end of class last time, we introduced extrinsic semiconductors. And extrinsic semiconductors are ones that we've doped in order to make them conduct. And we gave you two examples. We said that we can make it P-type or N-type. So if it's P-type, P-type versus N-type. P-type is something that you dope so it has holes. Then P, the number of holes, is going to be greater than the number of electrons, right? If you dope it N-type, then you've doped it in such a way that it has excess electrons, so the number of electrons is greater than the number of holes, right? And the way that we can do that, in the simplest way of thinking about it, is to start with silicon. Silicon has 4 electrons, which means it shares with 4 other silicons in order to get its 8. And if you put in something that's only got 3, like this boron atom, then that's going to have 1 missing electron or a hole. Meanwhile, if you put in something like a phosphorus, it's going to have 1 extra. Where is it? Oh, right there. Phosphorus has 5 electrons, so it's going to have 1 extra electron. So boron would make it P-type, phosphorus would make it N-type, for example. Okay, so with that said, our learning objectives for today are the following. We're going to calculate band gap once we know the carrier concentration as a function of temperature, right? So where does band gap come from? Like, how do you calculate that? We'll show you one way to calculate it. We're going to calculate the carrier concentration itself from something called a Hall measurement. We'll describe the basics of a few semiconductor devices. We don't have as much time as we'd like to spend on that. We'll describe how conducting polymers came to exist and how on earth these things actually conduct electricity, because polymers, it sort of breaks the rule. We don't expect them to conduct electricity. And then at the end of class, we're going to introduce dielectric materials. We'll describe about where does the polarization come from in these dielectric materials. And then once you have these, what do you do with them? And there's devices called piezoelectrics and other things that you can make out of these things that are pretty awesome. Okay, so let's start with a reading quiz for today. The first question is as follows. If you have a silicon semiconductor, that's a group 4 element, silicon, and you dope it with arsenic, which is a group 5 element, it should be A, N-type, or B, P-type. Okay, answers in. Some clicker tension. Okay, we move on? Let's move on. Okay, because it's group 5, it's got that 1 extra electron, it's going to be N-type. All right, next one. Piezoelectricity is coupling between which two things? A, is it magnetic field and electrical polarization? B, mechanical strain and magnetic moment? C, mechanical strain and electrical polarization? Or D, magnetic field and mechanical strain? Piezoelectricity. Okay, clickers in. Wrap this one up. Okay, definitely it is mechanical strain with electrical polarization. Okay, which is pretty awesome. Think about that for a minute. You squeeze something or you pull it apart and you temporarily create a polarization. That's the same thing you need to make a battery, right? So you can actually make energy harvesters that take advantage of straining a material. We'll talk about that later today. All right, the perovskite crystal structure is an especially good material for making high dielectric constants because it has large contributions from which of the following: electronic polarization, orientation polarization, or ionic polarization. Okay, clicker scores answers in. Okay, we're gonna wrap this one up. Okay, pretty even split. It's ionic polarization, this one. We're going to talk about why that is and why it's not orientation. Okay. So where we left off last time, we've already described that you can dope things and basically make them conduct, right? And it's helpful to think of these in terms of the band diagram. So again, the basic band diagram says you've got this band gap. And when you add dopants, you're adding just a few. You're not adding anywhere near as many as the host atoms. So the host atoms might be silicon. There might be like one dopant per million, right? It could be very, very small amounts that you're talking about. So because of that, you don't see big bands from the dopants themselves. You just see little impurity bands, right? You're able to put like one little impurity there or one little impurity there. So it's not a full band itself, but it is a spot, right? It's a spot where you could then take this electron, go up there and occupy that spot, okay? All right, so again, if you make something N-type or P-type, what this allows us to do is simplify our expression. For electrical conductivity, we said that the electrical conductivity is equal to the number of electrons times the charge of an electron multiplied by the mobility of each electron plus the number of holes times the charge of each hole, which is the same as the charge of an electron, times the mobility of a hole. That should be H. Right? What happens though is that if you dope it in such a way that you give it tons and tons of electrons, this term right here dominates over the other term. Or if you dope it the other way, you dope it so there's tons of holes, then there are way more holes than electrons, and you basically can neglect the first term in that case. So it allows us to simplify it, okay? Again, if it's the intrinsic case, under intrinsic conditions, then N sub I equals N equals P. That's basically saying every electron that starts out in the valence band goes up to the conduction band, so you have equal numbers of holes and electrons. That's the intrinsic case. But when we dope it, we're breaking that rule. We're saying that one can be much higher than the other, which allows us to simplify our expression, right? If it's P-type, because P is so much greater than N, we just leave off the N part of this equation. Technically, it's still there. It's just tiny contribution, really, really small compared to the P-type in this one, okay? Okay, this is what these things typically look like. Plotted on the y-axis, you've got N sub I. That's your intrinsic carrier concentration. And then that's plotted against temperature. Intrinsic carrier concentration, that's number of these things per cubic centimeter, right? So by the time that you're around room temperature, right there, you're already talking about significant amounts. When you heat these things up, it explodes, right? You have 1 billion times more carriers at 700 C than you do at room temperature in this material, right? 1 billion times more carriers, electrical carriers, okay? Why do these things heat up like that? Well, why do they increase like that? Because as you heat the material up, the Fermi-Dirac distribution, right? Remember, that goes from a really sharp distribution like that to one that looks increasingly sigmoidal like that. So you get a higher and higher fraction of your electrons that are able to reach that high level. Okay? So what you can do if you have a plot like this is you can plot it in a different way. Instead of plotting just Ni versus T on regular scales, if you plot the natural log of the intrinsic carrier concentration and you plot that against 1 over temperature, then the slope of this will give you the band gap. How do we know that? Because the number of intrinsic carriers, right, that's equal to N times the exponential of our, this time it's not an activation energy, it's the band gap. We think of it like an activation energy though. It's still an energy hurdle that has to be overcome, and then you're going to divide that by thermal energy. This time there's a 2 in the denominator, 2 kT as opposed to regular kT. But otherwise this looks pretty similar to other thermally activated equations that we've seen this semester for creep, for diffusion, for everything else, right? So again, you could rearrange this equation. I'm not going to take the time to do it in class because we've done it multiple times now. But you could rearrange this to see why the slope of this gives you the band gap. And I think you'll have a chance to do it on one of the homeworks. Okay? All right, I didn't make a clicker question out of this, so I'll just answer it right here. But it says, an extrinsic semiconductor, true or false, will not increase in electrical conductivity with increasing temperature at all temperatures. So basically, you dope something. The question is, if I heat it up, is it going to become more conductive at all temperatures or not? True or false? So maybe chat with a neighbor and tell me what you think. Okay, you've got an extrinsic semiconductor, so you've doped it. Will it keep on increasing or not? What do we think? Anybody want to take a guess? What do you think, Rob?
Well, at some point it's going to melt.
At some point it will melt. All right. So at temperatures below its melting point, let's consider those. Will it increase in conductivity or not? Jeff, you got an idea?
Yeah, I mean, thinking of a band gap diagram, the idea is if you heat it, more electrons go up. So, well, I mean, so theoretically speaking, it'll make more room. So I guess maybe the limit of there.
These are good questions. What do you think? Brandon, do you have an idea?
I would say it's probably practically true, but technically false. It's like you were saying, the other combinations in our equation are still there. It's just while we're ignoring them. So, like, even though those might be going up, they are going up.
Yes. Your logic is right. I think you said it backwards, but your logic is right. So, right, let's go to this image here, right? This is showing electron density, right? So basically the number of free carriers, right, on the y-axis, plotted against temperature. We talked about this last time. We said that this has 3 regions, right? You got this region below maybe 100 in this material. It's going to depend on your material, right? And then you've got that region in the middle, and then you got this region at high, right? So we'll call this region 1, region 2, and region 3. We called region 1 freeze out. We called this the extrinsic region. And we called this intrinsic. What you see plotted here is like 6 or 7 different materials. You've got pure silicon down here, or whatever this material is, right? That's your pure one down here. So that's the intrinsic carrier concentration, and that's increasing just like we saw right here, right? It's increasing with just this big curve, right? So that's happening. Meanwhile, you've got this funny behavior. These things are doped, and basically if you look at the numbers here, they're doped at higher and higher concentrations, right? So the more that you dope it with, you're increasing your carrier concentration. So technically what Brendan said is right. He said, technically because this curve should increase over all temperatures, your conductivity should increase over all temperatures. But what you're seeing is that practically speaking, there's a region in the middle where it doesn't increase very much because its contribution is still so small. Okay? Okay. So any questions on region 1, 2, and 3 in temperature dependence of these? This is a super common test question that I'll ask, is to describe what's going on there. Could you recap to your neighbor? Josh, you got a question for us?
Are there like different things happening in the material in each of the regions for why that's happening, or like why are they named differently? Or is it
the best way the best way to explain these 3 regions is to go back to your band diagram and imagine you have a fully occupied valence band, that you have a completely empty conduction band. And so if you were to start heating this thing up, we know that we could jump all the way across the gap, and that's what you're seeing in this big intrinsic line. But there are other things that can happen because you can dope it, right? You can dope it to have carriers down here, or you can dope it to have donors up there, right? This is what we call an acceptor, and this is what we call a donor, right? The acceptor at a small energy penalty is able to ionize and put an electron there and create a hole here. And this donor right here is able to ionize and give up its electron and then make that work, right? So this gap in energy, that small gap, corresponds to the small amount of thermal energy that you need to avoid freeze out, right? Freeze out is when you cool it down that even that jump isn't possible. Then you've got this big extrinsic region where basically all of these levels that you had by doping it, they're all filled, right? So nothing else can happen until you can start jumping the gap again, okay? Any questions on that? Yeah, Arthur?
When the electrons on the VB go to the first level,
okay.
And then you said that they jump up. Do they jump up to this blue line up here, or do they directly jump up to CB?
Good question. They're going to jump up just to these individual spots. Each one of these spots represents, let's call it a fixed number of acceptors. Acceptors might have two C's. Two C's? I think it's got two C's. And then this up here, these things, these are our donors. There's going to be a fixed number of donors. So once those have all donated their electrons, then you're done. You're not getting any more benefit from these things. And once your acceptors are all filled with electrons, you're done. That's why you've got this big flat region where nothing interesting is happening, because you don't have enough energy to jump the gap, and you have enough energy that all of these are ionized. They've either picked up an electron or lost their electron. Okay? So that's why you get these three regions. Arthur?
And so do the acceptors, when you cross that area of this flatness,
Yeah, this
do the
small region.
Acceptors jump to the donators, or do they jump directly down?
Good question, right? So this is something like a boron. Boron has 3 electrons, but the lattice wants to have 8. And so what it can do is one of its silicon atoms, one of the silicon electrons can go to boron, making the boron now negatively charged, right? That takes a little bit of energy to make that happen. But once it does that, now this hole is able to move through the material and conduct electricity. Alternately, up here, this was something like a phosphorus or an arsenic or something that had an extra electron. When it jumps up, now it's got a hole on it. Basically, it became phosphorus plus, right, with a positive charge. But it gave its electron up that can now move around in that conduction band. So what you don't have happening, it's not like an electron hops to here and then it hops up there. That's not what happens. You get an electron hopping to here, and now it's just active. That's now an extrinsic electron. It's able to conduct electricity. Okay? If you heat it up enough, it could jump up, right? Just like intrinsic conduction can start to take over and dominate. Okay?
And then will it jump up to the fixed donors, or directly to the CB?
I guess it would go to these spots first because, again, this is like a phosphorus that has 5 electrons. It loses one, so now it's positively charged. So technically, it would still like to grab an electron if one becomes available, right? So that is going to be a priority destination if you're going to start to hop up. You will start to ionize those. Okay? Any questions? Yeah, Jaron.
What's the direct relationship to electron density and conductivity? How do those two relate?
Good question. So electron density is N. If it's the intrinsic concentration, then it's N sub I, like we've got right there. If it's the extrinsic, then basically, let's say that like you dope something with 10 to the 20 carriers or dopants per centimeter cubed. Then you're going to assume if all 10 to the 20 of those ionize, then that's how many donors you're going to have, right? So again, N sub D, the book calls it N sub D. That's your number of donors. That's something like a phosphorus that has an extra electron. We're going to assume that that's equal to the number of electrons, right? N. And the number of acceptors, things like aluminum or boron that can pick up an electron, we're going to say that that's equal to the number of holes. That's the terminology the book uses. Okay? Again, we're assuming that all these things ionize. That may not be the case. Okay, any questions? Yeah.
Is there any like good animations we could like put like block down?
Yes, I will find one and get one posted for you. I'll do that. So let's say a few more words about this. Right here you've got no they don't. If you remember a homework or two ago, I had to use the BYU clean room calculator. You guys remember this? We did it for diffusion. That's for semiconductor diffusion. Because basically, imagine this whole table is silicon. If I want to introduce a channel in this material that has high conductivity, that's exactly what a transistor has, right? Transistors in all electronic devices, the silicon itself is not a great conductor, but they dope regions of it, like channels or pools or spots on it, and those now conduct electricity. So the way that you do that is you mask this thing. I could take like something and set it over it, and then I could bombard this with donor or acceptor atoms, and everywhere that it hits the mask is not going to get influenced, but things where those atoms can hit the silicon, they're then going to be able to diffuse into that silicon if you give it a heat treatment, and then if you peel away your mask, all of a sudden you've got a region that conducts and a region that doesn't conduct. And that's exactly what photolithography and clean rooms do. They basically have fancy machines that cover up regions of your material so they can lay down something, dopants, which will change the conductivity, and that allows you to create little tiny pathways that conduct or don't conduct. But what you're still relying on is diffusion to move these things into your material. You don't want it to conduct right on the surface, maybe. You want it to conduct in the top micron of your material, right? So it's still very important to understand how diffusion of these donors and acceptors relates to your host material, right? If diffusivity is really low, they're not going to be able to diffuse into it very far. Okay. All right, let's take a look here. This is electron mobility. Again, mobility, think of that like the friction forces that the electron feels as it moves through its lattice, right? So that's mobility. The higher the mobility, the less the friction, right? And here's versus temperature, right? So here you see 5 different samples, and they all show pretty similar behavior, right? They all reach a maximum, and then their mobility starts to decline. Mobility starts to decline for the exact same reason we described before in metals, right? As electrons move through a metal, the atoms are vibrating, and that's just going to act as a frictional force, right? Okay, let's talk about a Hall effect. We know that carriers are important. We can use them to calculate electrical conductivity. But how do you know if you've doped it the right amount? How do you figure out how many carriers are actually there at any given time? That's harder to do, but there's a great tool for it. It's called a Hall measurement. So if you remember from physics, you would have probably seen this before. It's like an intro physics problem. How it works is like this. You're going to pass a current through your material like that. Okay? So you've got a power supply, and you pass a current through your sample. So you've got electrons traveling through it. If your current's going that way, then your electrons are going that way. Right? So they've drawn this little electron right here, this guy, and he's moving up in this material, okay? But then they do something else. They apply a magnetic field to this. So they've got a magnetic field, how do we show that? Okay, BZ, there's a magnetic field going vertically up. So if you have an electron, which is a charged particle, and it's traveling that way, and you have a magnetic field that's pushing up on, that's in the up direction, this experiences what we call a Lorentz force in that direction, right? Got that backwards. Is that diagram backwards? The electron should feel a force, right-hand rule, right? The current goes, because they define current with right-hand rule, not electron motion, right? So current is going down, excuse me. Current's going down, electron field's going up, so your charged particle experiences a force that way. So yeah, your electron will travel that way. Does that make sense? We've seen this before? Let me explain it one more time. Okay. You've got a current traveling through your material because you hooked a 9-volt battery or anything else up to it, right? You induced a current, which is, the current is traveling that way, which means your electrons are traveling the opposite way. That's just the convention that we have, right? Because your current is traveling that way, the right-hand rule for a Lorentz force, which is the force that a charged particle experiences in a magnetic field, says that if the current's this way and the magnetic field is that way, that your particle experiences a force that way. Therefore, the charged particle is going to migrate that way. Vaguely familiar? Okay. So therefore, if your electrons are moving that way, you're going to actually build up a second voltage, one that you didn't actually intend for. It's called the Hall voltage, meaning if you measure the voltage from side to side of the sample, there will be a small but, measurable voltage there. And from that, you can figure out the number of carriers that must be moving through your material, right? Once you know the number of carriers, great, you know conductivity and all sorts of stuff, right? So it looks like this. The Hall voltage, V sub H, is equal to R sub H. That's a constant. It's your Hall coefficient, right? Times the current, times the magnetic field, divided by the thickness of your sample, T. T, that's your vertical thickness of your sample. So if you know those things, you can calculate carrier concentration, because R sub H it's going to depend on the number of carriers you have, right? R sub H equals 1 over the number of carriers, carrier concentration times their charge. Okay? Any questions, Zach?
So since the charged particles are going to that one side, would you say there's a fluctuation in current in the material?
Well, I mean, there's still a constant current traveling through your material. It's just that they're moving to one side when they're in the magnetic field as they travel through there. Just like a cathode ray tube, you guys have seen this in physics, right? You take in a vacuum tube, they would bombard electrons from one side to the other, and then when they would bring either an electrostatic force in there or a magnetic field, they can move that beam of electrons. That's all we're talking about here. They're just migrating from one side to the other. And because they migrate, you can get a buildup of a negative and therefore a positive on one side, and that's the Hall voltage. Okay? So what's great about this is that this is a super easy thing to measure. This experiment is not hard. You don't even need like a crazy magnetic field, right? You can use like non-electromagnets and you can do this measurement and get a pretty good number of how many free carriers you have, either p-type or n-type. Again, if this Hall voltage is flipped, let's say that instead of building up that it's just opposite. Instead of a positive voltage, you build up a negative voltage. You'd know that you have either p-type or n-type material because your charged particle is either negatively charged or positively charged, right? If it's either holes or electrons. Okay? All right, we're not going to spend a lot of time on this, but let's talk about a few basic semiconductor devices. You've probably seen these if you've taken ECE already. I won't be testing you on these. If anything, I'll ask very basic questions about it. But these, once you understand how band diagrams kind of come together, it all of a sudden lets you explain really complicated things like rectifiers. If in ECE you saw rectifiers before, what does a rectifier do? It takes something that's an AC signal, like this, and it turns it into something that's DC, right? It's direct current, it's not alternating. So this is critical. Every single one of us uses one of these all the time. Every time you charge your phones use DC power, right? But when we charge them, you have alternating current because that's more efficient to transmit power over long distances. So you have to have a rectifier, right? You have to have something that can convert from AC to DC, right? So this is how it works, and it's pretty clever, okay? So you start with a single crystal of silicon or some sort of semiconductor, right? And then we're going to dope it such that you've got a junction. On one half, it's p-type, and on the other half, it's n-type. So it looks like this, right? Let's draw a band diagram. In one case, it's p-type. So over here, this will be the p-type one, and this will be n-type. The p-type has lots of acceptors, right? It's got lots of these things like boron or aluminum that can pick up an electron to create a hole. Meanwhile, over here, this has lots of donors, things like phosphorus or arsenic that can create electrons by donating them. So what happens is that if you pass a current through this material, if you apply an electric field to this, and you force the electrons and holes to travel different directions, watch what happens. If we make the electrons travel this way, and we make the holes travel that way, we can cause recombination to occur, right? Think of it. You've got these electrons that are technically up at a higher energy level, right? They're in an excited state. If you make them travel spatially to a different part of the material that now has lots of holes, these electrons can fall down and recombine with this hole, right? In fact, it's energetically favorable for that to happen. So basically, you cannot have electrical current in that way, which means your electrons are traveling that way, because they're just going to recombine. Same thing over here. If your holes travel here, your electron's going to sense that a hole is nearby, and it's just going to fill that spot. What do we mean? We mean, going back to our drawing, a hole is like, let's say you've got this free electron right here. Let me change, green is fine. You've got this extra free electron, and if this was a hole, a spot where that electron could be, if it's traveling in the vicinity of it, it's going to say, why don't I just occupy that spot, right? There's no reason why it shouldn't. So that's exactly how rectifiers work. They allow current in one direction, but one direction only, because in the direction where it's not allowed, recombination occurs, and it gobbles up all your electrical current, because it just recombines. It produces heat instead, right? But if you move your electrons the other way, if you hook your battery up in the other way, then you can get electrons moving that way, and you can get holes moving that way. Okay? So this is a PN junction. It allows you to create a rectifier. Okay? Thomas?
Yeah. I don't know where is the alternating current here?
Okay. Good question. An alternating current, all that means is that if we applied a voltage across this thing, positive and negative, that's 60 times every second, that's switching. Right? And every time it switches in a way that causes electrons to move that way and holes to move that way, they just recombine. And when it switches the other way, they travel, right? So it takes a signal that should be like this, your voltage is like switching from side to side, and after you send it through this rectifier, you only get current during one of these cycles, right? So it'd be clear if they wrote this as like a current, right, instead of a voltage, right? You only get current in one direction because recombination occurs in the other direction, and that gobbles up your current. Yeah,
It's
Zach?
a limited voltage, right? Like you can't have too much voltage, otherwise it's just going to go back to.
Well, yes, you can overdo it. We're going to talk about that with transistors. Okay. So again, this is another diagram of exactly what I just said. Another way of drawing these band diagrams is to say that the Fermi level moves if you dope it p-type or n-type. This material, the dashed line, is the Fermi level. Again, that's where the electrons would like to sit at, but it's above their valence band. This one, the Fermi level, is closer to the conduction band. Therefore, this thing has lots of holes, and this thing has lots of electrons. And if you force the electrons to go that way and the holes to go this way, they're going to recombine. Right? And you'll actually give off light, which is an LED. That's exactly, this is an LED. An LED is just a PN junction, right? It's a thin little semiconductor that you have p-type and n-type. You force the current to go in a way that causes recombination. Energy must be consumed, so that's either going to produce heat or light or both. In an LED, it does both. That light comes off, and because this band gap is a specific, precisely known thing, you can make light with a specific, precisely known wavelength, right? You can make red lasers and blue lasers and green lasers. You can make Christmas sweaters, which you guys will see because I got working. It's kludgy. It's not what I intended, but it works, right? So that's an LED. That's all it is. An LED is just a PN junction. You're forcing electrons to fall down and fill the valence band from their conduction band, and it gives off light in doing so and heats up a little bit. Any questions? So these devices that seemed a little bit like magical and like only electrical engineers know these things, they're pretty basic. They're simple things once you understand the idea of band gaps and band diagrams. Let's do another one. Let's talk about transistors. Okay, how does a transistor work? What does a transistor basically do? They do a lot of things, but what do we use them for? Right? We use them to amplify an electrical signal oftentimes, or we use them as a switch. There's other things, but those are two things we use them for. Let's talk about signal amplification for a minute. Okay, this gets a little bit more complicated. Instead of just having one PN junction, here we're going to have a PNP or an NPN. So you're going to have two junctions back to back. The one in the middle, the key thing is it needs to be narrow. It can't be very thick, right? It needs to be pretty narrow. So here's how it works. You've got your N-type material, a very thin P-type material, and then you've got N-type material again. The voltage between this one, if you apply a voltage and you force electrons to move that way, recombination is going to occur. But if you apply a big enough voltage, some of them will sneak through. Okay? Right? Recombination is not perfect. These things can slide past each other. Right? So as some of them slide through, then once it gets from here to here, your voltage is the other way. You can apply a really big voltage drop across these two. So the few that do make it through this, middle region of terror where recombination occurs, they experience a large pickup in your voltage, right? So you can take a small signal and you can amplify it, right? Your total current is going to go down here. You are having recombination occur, but the signal that does come through gets amplified. So guitar pickups, this is one way that they work. There's other ways that you can make guitar pickups. Basically, that little vibration, right? The little tiny electrical signal, if you want to turn that into something larger, you want to amplify it, you need to have some of them make it through that base region. You need to start from the emitter region, that's going to come from your guitar. They have to make it through the base region, and the ones that make it through, you just amplify them, right? With your large collector voltage. Okay? Question?
Why would you even worry about why wouldn't you just have two end regions next to each other?
Because it'll only be the voltage that your semiconductor gives you, right? So this is what's called, there's a built-in voltage between your P and your N junction. This is way beyond this class. When you take electronic properties, you'll learn about it. But it's basically, it's got a fixed voltage. You can't make it go up to any arbitrary voltage. But if you apply a big voltage across this, then you can. So again, the key thing is that this base region has to be thin. If it's not thin, you're just going to completely recombine. You'll make a big old LED, right? And that's not very useful for you. Okay, let's talk about a MOSFET. A MOSFET is a metal oxide semiconductor field effect transistor. That's what it stands for, metal oxide semiconductor. So you've got three things. You've got metal, oxide, and semiconductor. That basically tells you what you're seeing here. You got a metal layer up top. That's this bluish thing. The brown layer is your oxide. That's not going to conduct electricity. And then down here you've got your semiconductor. And they call it a field effect transistor because when you apply a field to this, it switches on and off. This is so cool. Check this out. So you've got your basic substrate. This is silicon. Let's say you grew the crystal and it's p-type, right? You added some number of acceptors. So it's mostly p-type. But then, using any means you want, masking, ion implantation, there's lots of tools, you bombard certain regions of it with tons of electrons, right? Or donors, right? So this is mostly like, say, arsenic doped. These regions might be like boron doped. Other way around, right? This is boron doped. These would be arsenic doped, okay? Then what you've got this N-type, and you've got P-type. So you've got a PN junction built in for one thing, which means if you turn it on, you're just going to make an LED. That's not useful. But here's what's really clever. They apply a voltage between the gate, this is a piece of metal, on top of an oxide. The oxide won't conduct electricity. So instead of conducting electricity, what will happen? If you build up lots of negative charge here, because you hook it up to electricity, right? Then you'll build up a positive charge here. Oh, that's not what we want. We want it the other way around. We want the other way. So let's say we pull current away from this, right, by hooking up the other way. That induces a negative charge here. That negative charge is going to create a thin region right here that's no longer p-type, but rather it's n-type. So as long as you have a voltage across this thing, across what we call the gate, then you induce a tiny pathway that would normally be p-type and you make it n-type. So all of a sudden, now you can have conductivity from this region through here to that region. Right? So solid state memory, the beautiful thing that lets our computers start and restart so quickly compared to hard drives, is this phenomenon. They realized, hey, we can do this so small and so well, we can store memory there. If this is conducting, call that a 0. If it's not conducting, call it a 1, right? We can actually store memory with whether or not this gate is activated, right? So you have to have a way to make sure that this gate either exists or doesn't exist, and so solid state memory will decay over time, right? If you store your favorite, electronic copy of whatever on a jump drive, eventually it will go away, right? Magnetic memory has a much longer lifetime, but this is much, much faster, right? You don't need like a spinning disk head to like read and write magnetic moments. This is super, super fast. You guys don't seem amazed. This is amazing stuff. This is really cool stuff. IM Flash, like where you guys all want to get jobs because they pay bonkers money, is all about making these things, right? And I mean it, they pay really well. Okay, we could go on. I'm going to skip it for the sake of time, but there is like a ton more amazing devices. And in ECE, in your electrical engineering class, you learned about like and, or, and all these different type of logic operations. All they did is they put together transistors in different combinations to make all the logic operations that let computers be the amazing things that they are. Okay. Can I answer any questions before we move on? Again, I don't expect you to understand all the details of that. A question on the test might be like, what does MOSFET stand for? What is the gate doing? It's giving you a conductive path that would otherwise take something that's an LED and turn it into a conductive pathway. Okay, let's talk for just a second about microelectric circuitry. We can't not. It's the year 2017 and everything is tiny. My phone right now is vastly, like I'm sure thousands of times more powerful than the computer that let us land on the moon, right? That's because microelectronic circuitry has come about. It's pretty incredible. There's a guy named Richard Feynman. If you've never heard of Richard Feynman, do yourself a favor and YouTube him. Richard Feynman, fascinating guy, worked on the atomic bomb among other things. Fascinating guy. He, in 1959, delivered a lecture called There's Plenty of Room at the Bottom. Plenty of room at the bottom. He basically said, we are not taking advantage of miniaturization, right? We have, in this pen, there are billions and billions and billions of atoms, right? There's no reason that we can't be designing on a much, much smaller scale than billions of atoms at a time. We could do much, much smaller. So he set out a challenge. It was at, I think, the APS meeting, the American Physical Society. He set a meeting. He's like, okay, I'm going to do 2 challenges. First off, $1,000 if you can make a tiny robot, right? And he meant tiny. It had to be some smaller than, I don't know, some size, right? Because basically machines before then were still pretty big. And then he said, okay, I'll give you another $1,000. It's not a very good challenge, but that's what he did back then. If you can write the page of a book on the head of a pin, right? So how do you do that? So first off, a guy named William McLennan won the first prize. He was a watchmaker, and he basically used conventional tools, but he just like got it as small as he could. He technically like just squeaked below the size requirement for Feynman's challenge. He's like, fine, you win. But you really cheated because what I want is a paradigm change. I want something dramatically, crazily different, right? So up comes this guy named Tom Newman, a grad student. This is the best part. It wasn't the professor. It was the grad student. This is so amazing. He realized, just like we've been saying, right? We said that if you have a, let's say you've got a vacuum chamber and you've got a source of electrons and you're bombarding them down this channel. He said, well, if I apply like electrostatic forces to this, I can make this thing move a little bit up or down, right? Or magnetic field would do the same thing. He realized I can make a beam of electrons, bombard your sample, and if I just carefully control where I'm applying voltages on the sides of this beam of electrons, I can move it around. I can make it raster. And doing that, he wrote the first page of A Tale of Two Cities at 1/25,000th scale on the head of a pin, right? Using electron microscopy. If you look at it, you can read it. It was the best of times. It was the worst of times. It's not amazing, but he did it. He did this, right? And he really opened the door for massive electronic miniaturization. Nowadays, this is like chump change. 500 nanometers, we can do way smaller. The smallest transistor gates, they're moving it all the time. It's constantly happening. But I want to say it's around 5 nanometers. Anybody know this? It's somewhere around there. We can make tiny transistors. So instead of using billions and billions of atoms at a time, we're using hundreds or thousands, right? Something way smaller. This allows us to store tons of memory. Remember, and think about the first time that you ever used electronic memory, whatever that was, think of what the size was. When I was in college, I had a zip disk that had like 10 megabytes, and I was like, this is so sweet. I can hold all these pictures on here. Now 10 megabytes that's a single picture. That's kind of a small one, maybe. I don't know. So it's dramatically changed how we can do things. Here's a show. Oh yeah, right here. So this is the half pitch. That has to do with the size of a transistor as a function of year. And every year we just move these things smaller and smaller and smaller. But we have a new challenge for you. It's 1959 at the APS meeting all over again. You guys are the people that will make this happen now. How do we move smaller than 5 or 6 nanometers? What happens is if you have a field effect transistor, right? You have to have this drain region, this source region, you've got your gate region, right? And you create this channel right here that is either on or off depending on if you apply voltage. What happens when that gate region gets so small that the quantum effect of tunneling takes place? Tunneling is basically this. You shouldn't be able to transfer current from there to there, but it does it anyways because quantum mechanics, right? That happens. It's a thing and it's a problem, right? You start getting what's called leakage current where it shouldn't be conducting, but it is. So this is putting a limit. It basically says there is a fundamental physical limit to how small we can make these things. So what do? How can we make how can we make our devices smaller and smaller as we're approaching that limit, right? So if you've attended the IM Flash Tech Talks, this is a common thing they want to hear ideas on, right? 3D NAND logic, these things are allowing us to do clever things by building up instead of just smaller. They're building vertical memory infrastructure. But it's going to take clever folks like yourselves to come up with solutions for this, right? Okay, 7 minutes left. Let's start talking about, question, Rob?
Why don't we just entirely rely on quantum tunneling? Why don't we just completely do away with normal voltage, like normal current conduction?
So there are people that definitely work on this. It's called quantum computing.
Yeah.
It doesn't rely on tunneling. What it relies on is, right? Remember day 1 of the class when we talked about the quantum numbers, right?
Yeah.
Basically, it takes advantage of one of the values there. It takes the spin orbital coupling, right? So basically, you could store energy on where the spin is located. First off, you could do spin up versus spin down. That could be 0 or 1 in your computer, right? But then you can go even further. You can change the momentum of the spin. So basically, the spin doesn't have to be just up or down. It can be different directions. We didn't cover that in this class. But that could be how you store energy. The problem is, for that to happen, you have to have 3 things. You have to have a way to make right spins to some arbitrary direction. You have to have a way to make them stay put. And then you have to have a way to read those. And basically, we don't have a solution to any of those 3 problems. But there's kind of solutions. We can make it happen for like small amounts of time. We can make it either up or down. But small is like billionths of a second. We don't have a way to make it stay for a long time. So quantum computers don't work yet. But there's bright people working on them. A guy in our department, Ashutosh Tiwari, is working on them. Brennan?
If I recall, they've gotten quantum computers to work by chilling them.
Yeah.
The coldest point in the known universe.
Yeah, they kind of cheated, but yeah, they do technically work if you cheat a little bit. Okay, so far we've said that holes, which is a spot where an electron has been removed, that hole can move and conduct electricity. And we've also said electrons, but you can also have ions conducting. And it's a good thing because that's how all of our batteries in our phones work. Those are all lithium ion batteries, right? They conduct electricity by the lithium ion itself, not its electrons, but the ion itself being able to move through your material, right? So your overall conductivity, that's going to be contributions from ionic and electronic, right? And you can have materials that are completely electronic or completely ionic. So examples are like metals, right? Something like iron is going to be almost entirely electronic. Iron ions are able to move, but it's so much smaller than electronic that its contributions can be tiny. And the other way around, you can have materials like the materials used in battery electrolytes, like YSZ. Take YSZ. YSZ, that's yttrium stabilized zirconium. We've already talked about it. That's ZrO2, that you dope some yttrium 3+ on there, and that creates oxygen vacancies. That's a material where only oxygen 2- ions can travel through it. It basically does not conduct electricity, but oxygen ions are able to travel through it. So you can have your material be either or, and in some cases you can make it be both. It can conduct from both. If we are considering the ionic contribution, then the mobility has this term. Mobility is equal to the number of your carriers times their charge. What would the charge be for oxygen? 2. Right? So for every one oxygen ion that moves, you are basically getting double the electricity, right? This is better than electrons and holes, right? If you have something that has 3 charge or 4+ charge or something, you're getting more and more of a benefit in terms of how much they can move, right? That doesn't mean they're better because they depend on diffusion. And the diffusion of ions is going to be way smaller and way slower than the ability of your electrons and holes to move through a lattice, generally speaking, right? There's exceptions. There's fast ion conductors, and it's a good thing there are because we make batteries out of them. But generally speaking, ionic conduction is slow relative to electronic conduction. There are exceptions, okay? Okay, let's talk about polymers. This didn't exist until 1977. All these things are seriously not that long ago. We didn't have a polymer that would conduct electricity. In fact, we use polymers usually because they don't conduct electricity. This wire has polymer around it because we don't want to shock ourselves or short this thing out. This thing it insulates, it doesn't conduct electricity. The way that they found out how to make them is a clever guy in UCSB who won the Nobel Prize for it realized that polyacetylene is a molecule that conducts electricity. And then they said, well, what is it about this molecule that makes it conduct electricity? And they realized that it has alternating double and single bonds. If you have alternating double and single bonds across your backbone of your material, what that creates is it creates orbitals in the vertical direction that are either filled or half filled. And this looks like, if we go back to our diagram, this orbital that has above and below, basically you've half filled it by putting electrons in the bottom, but it's empty in the top. So this no longer has a band gap. This has your Fermi level right in the middle of a band, right? And once they figured that out, then they figured out all sorts of other ones that behave the same way. Nowadays, we have polymers that can conduct electricity. We can dope them N-type, we can dope them P-type. We can make transistors and LEDs out of them. This is a transistor or an LED entirely out of organic polymer materials. There's no silicon in that, and yet it's clearly emitting green light, right? They were able to dope it just by having these polymers. So now when you buy an OLED phone or OLED TV, OLED is an organic LED, right? So all of a sudden they exist today. Samsung sells a TV that you can put on a flat wall, and if for some reason you have any reason, I don't know what that is, but you want to curve that TV, that same TV, and put on a curved wall, be my guest. They can curve a little bit, right? But imagine what could be done. That's not here yet, but it's in the near future. Instead of having my notes written on paper or having my rigid laptop here, what if I could have a hybrid? What if I had something like a newspaper I could fold up and do whatever I want with it? And when I'm ready on the bus, I fold it out and I've got my iPad, right? So foldable phones are the future. You're seeing them already. Phone companies are already making curved devices, ones that can flex a little bit. It won't be long before we have electronic newspapers, right, essentially, because of this innovation. Yeah, Mohammed? Good question. I think I wrote some of it here. Okay, right here. They're pretty darn good, actually. Some of these things are about as quarter as good as copper. Copper is basically the gold standard. It's as good as it gets, almost. Silver's a little better, right? But they're twice as good based on weight, right? So if your conductivity is not the only thing that you care about, but it's conductivity and the density, how heavy your object is, these can actually be better. Okay, we didn't finish this today. We'll spend one more day on it, and then we've got Wednesday where we'll talk about anything that we didn't get to in this class, and we'll get ready for the final the week after.